Section 3.1 Orthogonal Trajectories. You've already learned about orthogonal trajectories before. Most of the stuff is going to be kind of like review for you for this section. So what we have here to start with this, for any differential equation, for DE differential equation, so far we learned about the nth order kind of differential equations, linear. We're going to take n parameter of family, and I'll explain that in a minute, family of curves, which will be given. What we need to do here, it's kind of like backwards of what we did before. Before they give us a differential equation and then we try to solve it. We are looking backwards to find the nth order differential equation if the solution is given. Just for this part of the section. For example, let's say they ask us to find the differential equation of this solution, CE to the x. Well, to do that, what we need to do is differentiate both sides. To get dy dx equals CE to the x. But CE to the x is the same as y, so then you get dy dx is y. That's the differential equation. And before we start with orthogonal trajectories, we need to introduce what orthogonal curves are about. Orthogonal curves. So we say two curves, let's call them C1 and C2, are orthogonal. Orthogonal is like a perpendicular at a point A, which is their point of intersection, if their tangent lines are perpendicular at that point, at point A. So, for example, if you have a curve like this and another curve like this, so this is C1 and that's a C2 curves. You have a tangent line to C1 and another tangent line, tangent to C2. This, if they are perpendicular, the two tangent lines in green are perpendicular, then the two curves C1 and C2 are orthogonal. So call this T1 and T2. So T1 perpendicular to T2, then C1 and C2 are orthogonal. Let's look at an example. Show that the curves x squared plus y squared equals 25 and 3y equals 4x are orthogonal at their point of intersection. Point or points of intersection. How do we do this? There are some steps to follow in the solutions. The first step, find point or points of intersection. Two, find dy dx for both of them. Recall, two lines are perpendicular if they have opposite reciprocal slopes. So first thing, we find their point of intersection. From the 3y equals 4x, you can solve for y, which is 4 over 3x, and substitute into the equation, the other one, x squared plus y squared is 25. Let's see what we get. X squared plus, this is 4 over 3x squared equals 25. X squared plus, this is 16 over 9x squared is 25. Add them together. You get x squared is 9, so from here x is plus or minus 3. When x is 3, substitute that back into the equation of the line. Y is 4. And when x is negative 3, y is negative 4. So these are the points of intersection of the two curves. They intersect at 2 points. And as you know, one of them is a straight line and the other one is a circle. So let's look at them at one point at a time. At this point, 3, 4. What do we have? Notice what I said in the steps. We first find their points of intersection, then find dy dx for each one of them. So for 3y equals 4x, 3 dy dx is 4. So dy dx is 4/3. That's for the line. So I'm going to do like this, line, circle. This is 4, dy dx is 4 over 3. For the other one, the x squared plus y squared is 25. Differentiate both sides, 2x plus 2y dy dx equals 0. Divide everything by 2, so x plus y dy dx is 0. So dy dx is negative x over y. So dy dx is negative x over y. Now at that point, x is 3 and y is 4. So now compare these two results, because dy dx at a point is the slope of the tangent line. So they are opposite reciprocal. So I'll give you some time, or you can try to work it out the same way at -3, -4, and get dy dx for both of them. We may continue now. So dy dx is going to be the same here, regardless. And for dy dx, for this one, it's again -x over y. So it's -3 over -4, 3 over -4. So they are also perpendicular. So since the two tangents at the points of intersection of the two curves are perpendicular, then the two curves are orthogonal. Another example, show that the family of curves y equals c1x cubed. Why we call it family of curves? Because for every single value for c1 you get a curve. Every time you choose a value for c1 you get a curve. Show that the family of curves y equals c1x cubed is orthogonal to each curve in x squared plus 3y squared equals c2, which is positive. So c2 is positive. And how do we do so? From the first curve, from y equals c1x cubed, we can solve for dy dx, which is 3c1x squared. And keep in mind c1 is y over x cubed. So what do we get from here? I'm getting the slope here by finding dy dx. 3 times, I want to get rid of the c1. I replace c1 with y over x cubed times x squared. So I replace this c1. Dy dx is 3y over x. That's for the first one. For the other one, we can also differentiate both sides to get 2x plus 6y dy dx equals to 0. And we need to solve for dy dx. So dy dx, the 6y, is -2x. So dy dx is -2x over 6y, which is -x over 3y. That's what dy dx is. -x over 3y for this second curve. Notice these are negative reciprocal, right? Negative reciprocal. So we say the same thing. Since the tangents are perpendicular, then the curves are orthogonal. Okay, now we are going to look at the orthogonal trajectory. Okay, orthogonal trajectory. So what do we do here? Orthogonal trajectories, when we say when all the family of curves, call it f of x, y, c1 equals 0, intersects orthogonally all curves of another family g of x, y, c2 equals 0, then the families are orthogonal trajectories of each other. That's the definition. And the big question is how to find orthogonal trajectories. For example, find orthogonal trajectories for the curve y equals c1 over x. We need to find orthogonal trajectories for this one. First thing we do is solve for c1, which is xy if we cross multiply. And from the same given curve or family of curves, we can differentiate both sides, dy dx. You can write this as c1x to the negative 1 for easy differentiation. We get a negative down, c1x to the negative 2. So that would be negative c1 over x squared. But we need to have an answer with no c's in it, no c1s. So dy dx equals negative xy over x squared. So dy dx is negative y over x. So this is the differential equation, for, you know how we said in the definition two families of curves, f and g. So this is kind of like the differential equation for the first family of curves. Okay, that's the first one. Now for the second one, family of curves, it must be what? In order for them to be orthogonal trajectory, dy dx must be the negative reciprocal of the boxed answer, which would be x over y. So these two are the orthogonal trajectories of each other. Now, how do you find it out, the curve, this second curve? What's the second curve? So we have this curve given. We need to find the orthogonal trajectories for this one. So we need to find the second equation or the second family of curves. So this one is given. I need to find the next one. So the steps are the following. We find dy dx for the given one. Then we do opposite reciprocal. From the opposite reciprocal, from this one, we can solve this differential equation. So we can obtain the equation for the family of curves. So solve this differential equation by cross multiply. We get y dy is x dx. Integrate both sides. So I'm using separable. This becomes y squared over 2 equals x squared over 2 plus c, or I'm going to do c over 2 just for fun. If you multiply everything by 2, you get x squared plus c. And then you can leave it like that. So this one, this family of curves is the orthogonal trajectory for the given family of curves. So we can say y squared equals x squared plus c is the orthogonal trajectory for the given one was c1 over x. C and c1 are constants. C and c1 are constants. Anyone has any question for me? You probably noticed that you already learned all of this back in calculus. This is the idea behind this section is just to show you an application of how we work with differential equations. Any questions?